Everybody, this is a lecture on the origins of electromagnetism and the connections between electricity and magnetism. Coming into this, you should have a pretty basic a pretty decent understanding of electric forces, circuits, and just basic bar magnets, north and south pole, attract and repel, and the magnetic fields that they produce. But this lecture is going to be a little bit different. I'm going to give a very, very brief introduction. But most of the lecture is going to be discussion of demonstrations in other YouTube videos. So I'm going to include a link to an experiment or a demonstration of a phenomenon. And then I'm going to discuss the implications of what happens in that experiment. And then at the very end, we'll summarize. So it's not really going to make any sense. It's not going to be that useful unless you actually watch the other videos that are included, that are linked. So let's get started. So back in the 1800s, we understood electric forces, or the late 1800s at least. We understood electric forces. We understood that how magnets work. They could both produce attractive, repulsive forces. They were kind of similar, but they acted on totally different things. They were essentially different forces, or at least we thought they were totally different forces, despite their similarities. That changed in the early 19th century, the early 1800s. There were a few experiments that were done. There were a few phenomena that scientists noticed that indicated that there might be some connection between electricity and magnetism. We're going to look at some of these phenomena and more. Here are two of the most important early scientists in the connection between electromagnetism. This is Henry up top, and this is Michael Faraday down below. A couple of experiments, or a couple of phenomena that kind of were essential to discovering this electromagnetic connection was the deflection of a compass needle when you ran a current through a wire nearby. The fact that wires in circuits would actually attract or repel each other, but only when there was a current running through them. And the fact that if you had a magnet near a circuit, that would actually affect or could affect the currents, the electricity running through. How can these be true? Or how can that happen if magnetism and electricity are totally separate forces? So let's look at our first phenomena. Really, two phenomena. The first up here is the deflection of a compass needle by a current. And it doesn't show the fact that if you reverse the direction of the current, it reverses the direction of the compass deflection. And also we're going to look at the magnetic field pattern around a wire in this video. So take a minute to watch these videos. Okay, so these two phenomena show essentially that when we have currents, that those currents create magnetic fields. The first video kind of shows the direction of the magnetic field, shows the fact that that magnetic field appears and disappears when we turn on and off that current. The second one shows us the shape of that magnetic field. And so the magnetic fields are going to form loops around our wire. And the direction of the electric current determines the direction of the magnetic field. If we reverse the direction of the current, we reverse the direction of that magnetic field. So currents create loops of magnetic field around them. Let's look at phenomenon number 2. Well, actually, here's a visual of the magnetic field that's created around a wire. Here we have a wire with current running through it like this. And the blue rings represent the magnetic field lines around it. They still form closed loops. They're just going around the wire. Reversing the direction of the current should reverse the direction of our field, and we can kind of see that in these two diagrams here. Now, in both of these diagrams, we have a current right at the center. On the left diagram, the current is going into the page. That little X with a circle indicates it's going into the page. It's a vector notation that's used when you're trying to do 3D stuff on a 2D page. So when our current is going into the page, the magnetic field lines go clockwise around that current. And when our current is coming out of the page, a circle with a dot is the symbol for a vector coming out of the page, or out of that surface. The magnetic field lines go counterclockwise. And that's kind of an annoying thing to memorize. There's not an easy way to memorize that. Into the page, clockwise, out of the page, counterclockwise. But there's a really easy way to do it. It's one of many right-hand rules that we use in physics. I'm just going to briefly show it to you. And you can basically use your right hand to determine the directions of all of these vectors. If you take your right hand and you place your thumb in the direction of the current around the wire, then your fingers actually wrap around in the same direction of the magnetic field. If you curl your fingers, they can only curl in one direction, and they're going to curl in the direction of that magnetic field. Also, we could do the reverse. If we know the direction of the magnetic field, we could curl our fingers around in the direction of the magnetic field, and if we give a thumbs up, that thumb points in the direction of the current. This is one of many right-hand rules that we use in physics when we're dealing with kind of 3D combinations of vectors. But importantly, you have to use your right hand. Okay, here's electromagnetic phenomenon number 2, and this is really just an extension of phenomenon number 1. It's the magnetic field of a coil of wire. We have a single wire, we run a current through it, but that wire is looped around on itself over and over and over and over again. So it's essentially just a loop of current. We wrap it around itself many, many times to essentially amplify that current through that space. If we have 2 wires going to the right, and each carries a current I, then the total current going to the right is 2I. So take a look at that video. Okay, so from this video, we looked at those iron filings. We can infer that a loop of current creates the same magnetic field as a bar magnet. If we have a loop of current, we get a dipole-shaped magnetic field. And so you might ask now, are permanent magnets made out of loops of current? And we're not going to answer that question right now, but there is a connection there between kind of permanent magnets and microscopic current loops. So here are just some diagrams that show us what's going on. Let's start over here. Notice if you use the right-hand rule on any part of this loop of current, it'll give you the direction of the magnetic field at that point. So right here, you can see the magnetic field loops around this way, underneath, like that. We can do this all around our loop of current, and we get these circular field lines that loop around. And if we add them all up, we see that the direction of our magnetic field, well, we get this shape, which is our dipole shape. And when we do this, this is called an electromagnet. We're using electricity to create a magnet. Since the magnetic field is the same as of our magnet, the magnetic forces are going to be the same as of our magnet. The other great thing about electromagnets is you can vary the intensity and direction by just changing the current. And you can also turn them on and off, unlike a permanent magnet, unlike a permanent bar magnet. Another cool thing about coils of wire and loops of current is, one, we get a uniform field inside of our loop of current, or inside of our coil, or it's approximately uniform at least. And it's also really high intensity if we wrap our wire around a lot, because we're essentially getting more current. There's also another right-hand rule that you can use to determine the polarity of the electromagnet. If you wrap your fingers around in the direction of the current, as in this diagram, then your thumb points in the direction of the north pole of that electromagnet. So the converse is also true, or the reverse is also true. If you point your thumb in the direction of the North Pole, then your fingers will tell you the direction that the current is flowing around your loop of wire. But it only works with your right hand. Let's take a look at electromagnetic phenomenon number 3. This involves parallel wires that we run currents through. And we're going to run currents through in the same direction and the opposite direction, and no current at all, and look at the effects of those currents. Okay, so what did we see here? We saw that if we put, if we had parallel wires and we sent currents down in the same direction, we get an attractive force. The wires move towards each other initially. And if we put them in opposite directions, we got a repulsive force. The currents were opposite, the wires repelled each other. And so this might be some sort of new electrical force or current type force. But using what we know about basically the fact that magnetic fields are produced by these wires, the magnetic field can be the mechanism for why these things are attracted or repelled. The wires are electrically neutral, so there can't be an electric force. But because each wire produces a magnetic field, when the current is running through it, that magnetic field is applying a magnetic force to the other wire. So currents can apply forces to other currents, and currents are affected by magnetic fields. If we place a wire in between a rightward pointing magnetic field, as in this diagram, we run a current in the direction that the current is running here, it's going to feel a downward force. It's going to be weirdly deflected perpendicular to that field. And we can see that, we can see if we run these wires parallel to each other and run the currents in the same direction, they do attract. We have this attractive force between the wires due to that magnetic field. Okay, phenomenon number 4. This is actually several phenomena that are all collectively different types of electromagnetic induction. We're going to see induced current by moving a magnet near a wire. You're going to see the current induced by a changing magnet again later. You're going to see an electromagnet turned on and off to create a magnetic attraction. You're going to see electromagnetic induction, which is kind of a combination of all that, used to transfer mechanical energy from one moving object to another. It's going to involve a moving magnet that induces a current in the coils. The current in the coils is then going to induce a magnetic field in the second coil. Because there's current running through it, it's going to become magnetic when there's current. And then that magnetic field is going to apply force to the second magnet. So take a look at that video. Okay, so from this, we have a couple of hugely important ideas. Importantly, if we have a changing magnetic field, we can create a current. That's the only new idea here. But the implications are huge. Because we know that a current produces a magnetic field. So if we have a changing magnetic field, we create a current. If that current is changing, that's going to create that current is going to create its own magnetic field, and if that current is changing, that magnetic field is going to be changing and can create more currents. And these are the principles behind electromagnetic induction. These are the principles behind all of our power generation and production, behind motors and generators. Here in this GIF, we have a wire moving through a magnetic field. And this is essentially the same as a magnet being moved near a wire. And as it's moved near that magnetic field, we get a current that moves through our wire. Here, this is essentially a generator. We have a magnet, which is really just there to produce a magnetic field. And inside that magnetic field, we have a loop of current. If we move that loop of current within that magnetic field, if we rotate it, or sorry, that loop of wire, that coil, if we rotate it, it induces a current. So just by moving this, by cranking this loop around, we get an electrical current. And this is exactly how almost all power generation works. We spin something in a magnetic field, in a coil of wire, to create alternating current, AC. A motor is just the reverse of that. A motor involves applying a current, which will, well, in this case, that current is creating a magnetic field in this coil of wire here. And the magnetic field of that coil of wire, and that basically electromagnet, is causing the coil of wire to spin. And that's all a motor is, using current to create magnetic field, to create mechanical motion. Okay, so let's look at this last phenomenon, the magnetic force on a moving charge. Okay, so from this, importantly, we can see that if we have a magnetic field, it applies a force to a moving charge. And the video didn't really go in depth, but if your charge isn't moving, you don't get a force. What's also interesting is that our charges in a magnetic field change direction. It causes our charges to bend, to deflect, causes that electron beam to turn. And in a uniform magnetic field, our moving charges actually are going to undergo uniform circular motion if they're sent in perpendicular to that field. So from a magnetic field, we can get circular motion. This is just kind of an illustration of what's actually happening. Weirdly, the magnetic force on these moving particles is perpendicular both to the magnetic field and the direction of motion. So if we're going perpendicular to that magnetic field, we actually end up with a force that always points perpendicular to our motion. We get circular motion. And a cyclotron uses a large uniform magnetic field to get particles to spin, to rotate in circles. This is a cathode ray, as you saw. Actually, all old TVs were made out of cathode ray tubes, basically electron guns, that shot out electrons, and you could use magnetic fields to cause the beam to sweep across the screen. Those electrons would interact with phosphors on the screen and cause them to radiate light, which is how all the old TVs worked before flat screens. Okay, so in summary, we have two ways of thinking about magnetism and electricity, the microscopic way and the macroscopic way. The microscopic way says, if we have moving charge, that's the source of magnetic field. In all of our demos, we were looking at currents creating magnetic field, but current is just moving charge. So moving charge creates magnetic field, and magnetic fields affect moving charges. Our magnetic fields affected our current-carrying wires, moving charges, and they affected the electrons that were just traveling through space without wires. So there's our microscopic view of the origins. And macroscopically, what this means is electric current induces magnetic fields, and changing magnetic fields induce electric currents, which is called electromagnetic induction. Now, this is a lot of information, but if you essentially know these big concepts and can recognize some of the experiments, then you should be good. One last interesting bit. Electromagnetic induction is actually responsible for everything we see in the universe. Because if we have a changing electric field, we get a magnetic field. And if we have a changing magnetic field, we get an electric field. So once we have an oscillating electric field, it self-propagates out, as in this diagram. We get an electric field and a magnetic field and actually just travel out like a wave. And this wave in the electric and magnetic field, the electromagnetic field, is called light, or electromagnetic radiation. And it's all just because of electricity and magnetism. Hope that's helpful.